Welcome back to Integral Calculus. In this video, I want to talk about exponential functions. The ideas in this video are just going to bring together a couple of things we've been talking about in previous lessons. First of all, we established this natural logarithm function, and we know that the derivative of the natural log of x is 1 over x. The second thing we know about natural logarithmic functions is the inverse. If y is the natural log of x, then x is e raised to the y power. The exponential and natural logarithmic functions are inverses of each other. And then the third thing we've established is that for any invertible functions, the derivative of the inverse is 1 over the derivative of the original function evaluated at the point of the inverse. Running out of space here. I guess I should get my head out of the way so that we can start using these things. All right. So combining all of this together, we can establish pretty readily that the derivative of the exponential function e to the x is going to be 1 over the derivative of the inverse function. Well, the inverse function is natural log, and the derivative of natural log is 1 over, and then it would be x, but we evaluate at the inverse function whose derivative we're taking. So the derivative of e to the x is 1 over e to the x. And the reciprocal of something is that original thing. The more general rule, if I have e raised to some power u, which is probably a function of x, then following the chain rule, I'm going to have the derivative of that exponent, u prime, multiplied by e to that original power. That's it. That's our differentiation rule for exponential functions. When you take the derivative of an exponential function, you get the same function back. If it's a more complicated function, well, it gets a coefficient. And from that, we can establish the integral rule. Right, just integrating both sides of that expression will give us e to the u du. Integral of e to the u du is equal to e to the u plus c. All right, that's it. That's all there is to it. If I want to take the derivative of e to the 7x squared, well, I'm going to have the derivative of 7x squared, which is 14x, multiplied by e to the 7x squared. That's it. That's all there is to it. If I want to try to integrate x e to the x squared dx, well, I might want to try a substitution here. If you're very comfortable in what you're doing, you might be able to do this without a substitution. But if you're not very comfortable with it, I'd suggest writing it out. Let u equal x squared. Then du is 2x dx. We've got the dx, we've got the x, we need a 2. Of course, I can just multiply by 2 and multiply by 1/2. That doesn't change anything. Since 1/2 is a constant, it can go outside of the integral. So I get 1/2 e to the u plus our constant of integration, and then plug back in u was x squared. All right, derivatives and integrals of the natural exponential function are very simple. There is one other, what happened there? There is one other property that we talked about in a previous lesson. If I have some other base a that I'm trying to raise to a power, we established that I can write that as e to the a if I have some other base a that I'm trying to raise to a power, we established in a previous lesson that I can write that as e raised to the x times the natural log of a. And just thanks to properties of exponents, that does in fact simplify, right? You can bring the x inside the natural log, so it's e to the natural log of a to the x, and then the e and natural log cancel each other out, leaving you just with a to the x. All right. But then we can use that to establish some differentiation rules. Well, the derivative of a to the x is the derivative of e to the x times natural log of a, using the differentiation rule we just established. The derivative of x times natural log of a, which is just natural log of a, times e to the x natural log of a. And then, of course, e to the x natural log of a is just a to the x. So this can be written as the natural log of a times a to the x. Or, if you want the general purpose rule, a to the u is going to be natural log of a times u prime times a to the u, right? Just using the chain rule and saying if there's something else in that exponent, you're going to need to take its derivative. And then flipping that around, I'm not going to go through and try to figure it out. If I have the integral of a to the u du, well then I'm going to need to get rid of this natural log of a, which means I'll divide by it. It'll end up on the other side. 1 over natural log of a times a to the u plus our constant of integration. All right, so if I want to differentiate 7 raised to the x power, well, according to my formula, this is going to be the natural log of 7 multiplied by 7 to the x power. And if I want, here's an interesting one. If I want 2 raised to the 2x power, well, the rule says it's going to be the natural log of 2 times the derivative of 2x, which is 2, times the original function, 2 to the 2x power. And the reason I said this is interesting is because if I used properties of exponents here, 2 to the 2x is the same thing as 2 squared to the x, which is just 4 to the x. All right, well, the derivative of 4 to the x would be natural log of 4 times 4 to the x. So we have two different ways of writing the same derivative. But that's okay. Because if you take natural log of 2 times 2, you can use properties of the logarithm to write that as the natural log of 2 squared, and 2 squared is 4. And then if you take 2 to the x and you do the same thing we did before, you can again get it written as 4 to the x. So it's two ways of writing the exact same expression. There's no right or wrong way between them. One last example. If I'm trying to integrate 3 raised to the power 2x plus 5, well, in this case, I'll probably try a u substitution. As I mentioned earlier, if you're very comfortable with u substitutions, you can probably do this in your head. But if you're not comfortable with u substitutions, and I don't expect you to be comfortable with u substitutions at this point, writing it out is probably a good idea. All right, so we need an extra factor of 2. We can introduce that by also putting in a 1/2. And this integral becomes 1/2 integral of 3 to the u du. The 1/2 stays. The integral of 3 to the u is going to be 1 over the natural log of 3. And then we multiply by 3 to the u and add our arbitrary constant. There's always some question. Should I be multiplying the arbitrary constant by 1/2? Should I be multiplying the arbitrary constant by 1 over the natural log of 3? And remember, it's an arbitrary constant. It doesn't matter. If you wanted to multiply it by 1/2, that means just choose double the arbitrary constant you would have chosen otherwise, and you get the same thing you get either way. So it doesn't change anything. There's no reason to go about doing it. All right, I am going to combine. Why did I switch to the blue pen? I am going to combine the fraction into one thing, 1 over 2 times the natural log of 3, multiplied by 3 to the substitute back in. U was 2x plus 5, and then plus arbitrary constant. All right. And with that, I'm going to leave you with a bit of a challenge. It's not that bad, but it's going to require a little bit more thought than we've put into the ones so far. Here I have the derivative of pi raised to e raised to the x. It's a tower of powers. But if you stop and think about it for just a second, it shouldn't be that bad, just following the rules we've established in this video. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.